Hello. Hi everyone. Welcome to our seminar today, How to Build a Quantum Supercomputer, Scaling Challenges and Opportunities. My name is Lior Mishan and I'm the Director of Product Outreach at Quantum Machines. I'll be your moderator for this session. And with me are three distinguished guests, Professor John Martinez, Dr. Jonathan Cohen, and Dr. Masoud Mohseni. As you can see, we have a very packed agenda planned for the coming hour. We start with John presenting a short intro, then going over qubit hardware fabrication. Jonathan will continue with control and decoding, and Masoud will proceed with software and research estimations, and then John will take us to roadmap and conclusions. We then have some time for the Q&A, and of course, you're welcome to leave us questions afterward, and we'll address them after the session. The session is, of course, recorded and will be available on demand on Quantum Machine website. And for questions, please ask your question in the Q&A tab. A bit about our speakers. Professor John Martinez is a distinguished physicist known for his contributions for quantum computing, particularly in the development of superconducting qubits. As part of his work, he played a leading role in Google's quantum supremacy experiment in 2019. Beyond his research, he remains dedicated to mentoring and collaborating with the next generation of scientists and engineers with the goal of making practical quantum computing a reality. And again, I'm sorry everyone that I've shortened the bios to really leave us time for the session. Dr. Jonathan Cohen is a physicist, entrepreneur, and co-founder of Quantum Machines, where he serves as Chief Technology Officer. As a CTO, Dr. Cohen enable high-performance quantum computing, advanced hybrid quantum classical architectures, and accelerated realization of NISQ and fault-tolerant quantum computers. Dr. Masoud Mohseni, a co-founder and head of emerging machine intelligence, which encompasses the HP Quantum and physics-based Gen AI teams. He is leading a consortium for designing and building quantum supercomputer for large-scale quantum simulations and quantum modeling. Formerly, he led Quantum Machines' leading team at Quantum AI Lab at Google and MIT. And by this, we'll switch to you, John, to start the presentation.
Next slide. Okay, thank you. Thank you very much for attending today. Today we're going to talk about a position paper, our collaboration posted back in November. This is a more recent post where we've updated the paper on how to build a quantum supercomputer. And what we've done here is thought about the full stack, going from making devices all the way up to algorithms and making a supercomputer with a collaboration, and to give enough detail that you can really understand what it takes to build a quantum computer. And we wanted to describe how we think we're going to do this, and we also want to motivate other qubit types to do the same thing, which I think will really give a lot of focus to the field that really figure out how to build a quantum computer. Now, in this, we're talking about a full stack, and we're going to be collaborating with big semiconductor companies who are used to building computer components and computer systems, starting, let's say, at the hardware end with Applied Materials making devices, going all the way up to HP, Hewlett-Packard Enterprises, who builds supercomputers, and in between. Now, besides talking about hardware, the software stack, we also have a stack having to do with the kind of expertise of the various institutions. Big companies, startup companies like Colab and Quantum Machines. We're also collaborating with national labs and universities because they have also a lot to offer us in terms of research and development of doing this. Next slide, please. Now, in building a quantum computer, a lot of the people are just thinking, well, what do we have to do in the next year or two to do the next paper, to get the next funding round? That's really good. But in our view, we also have to be thinking about long-term, starting at, let's say, 100 qubits or so, and how are you going to build a system up to 100,000 or million qubits? And the reason you need to do that, it's very simple, is that as we go ahead and scale up these systems, we have to make sure what we're doing right now or a few years from now is upward compatible into building a big system. If at some point the progress is going to stop and we're not going to get to the end product we want, that's going to be a problem. Now we have a list here of all the things, the summary of things we have to do at the various levels. We're going to talk about these things as we go ahead and give the presentation. But just keep in mind, there's lots of criteria you have to think about and new criteria that you have to think about as you scale up. And we'll talk a little bit about that as we proceed with our talk. And of course, you can read about it in the position paper. Next slide, please. Okay, now in talking about doing this upward compatibility, you have to kind of figure out what is it, the system requirements that you did. So what we did here is in the paper, we talk about kind of some of the important benchmarks that you have to do for the qubits that connects to the algorithms up ahead and connects to the hardware down below. And in the paper and later we'll describe this, but this is a table of what we think we have to build a useful error-corrected quantum computer. And these are the kind of parameters you want anyway, even for a NIST quantum computer. So we have a bunch of criteria, but the important thing is, first of all, there's a baseline, which is kind of where we are right now. And I think the latest Google experiment is a good example that's roughly corresponds to that. Then we have target parameters that we believe, which is what you're going to need to build, which is a quantum computer that can be useful. And then a lambda 18, which is about a factor of 2 better than that, which we really think is what you're going to want to do in the long run. So you want to target, you want to make sure you can get to that in the long run, but the target is a good parameters that we want to get to right away. And these are for the superconducting qubits. You can see that the numbers are better than where we are right now, but by a reasonable, modest amount. Not that it's easy to get there, but that's what we're really thinking about achieving as we build the quantum computer. Next slide, please. So that slide was talking about some particular parameters. I'd like to here talk about the most important 4 important qubit metrics that we really need to get to. Of course, for system engineering, there's hundreds of things we have to get right, but these are the big ones that we have to get right. And it's a good way to compare the various quantum hardware modalities there are. So there are qubit errors, which I think people understand, the number of qubits, and we have to make sure it's scalable. The connectivity of the qubits, kind of more is better, and then the speed. Now, on the connectivity, okay, so for the benchmark targets that we're reaching, we're looking for a 2-qubit error in the 10 to the minus 4-ish range, about 0.03%. That's going to get the lambda 18 factor that we want. And then in terms of the number of qubits, we're going to base it on a module size that's about 20 qubits per wafer module, and then we can tile it and connect it up to make better. In terms of connectivity, we're going to look at the surface code with 4 nearest neighbor qubits, and 4 nearest neighbors instead of a smaller nearest neighbors like what IBM is doing, is because you want to make your design tolerant to individual dropouts. Because you're not at this point, it's probably we're not going to make everything with 100% yield. And in fact, with 4 nearest neighbors, you can think about 1% of the qubits dropping out. It's okay. But the important one I want to emphasize here is speed. Superconducting qubits 50 nanosecond gates operate in parallel. That's kind of what the speed you need to do is to run realistic algorithms. And that's in the paper and will be talked about later. You really need speed to run useful algorithms, okay? For example, if you take atoms, like neutral atoms, ions, it basically takes about 100 microseconds to move them. That's 2,000, maybe up to 10,000 or 100,000 times slower. You take the time to execute these algorithms and you multiply them by a few thousand, you're not going to be able to run the utility scale algorithm. So this is really important and why solid state qubits are favored for long-term quantum computing. Now, of course, they're fast and you have a much more challenging control system, but frankly, you just have to live with that because you need the speed. Next slide, please. Okay, so now I want to talk a little bit about our approach on the hardware. And the basic issue here is most superconducting fab efforts are incremental. We're using shadow evaporation. That's really dirty. We need to do better. And a way I like to illustrate that is the plot of the number of qubits from the Google group over the last decade or so, starting with 2 experiments I was involved in, the error correction and quantum supremacy at 9 and 53. And then, of course, the third data point very recently, this surface code experiment. And what I like about these experiments is the qubits are improving at every generation, and you're doing more and more state-of-the-art experiments. So the number of qubits is kind of a good proxy for improving it. Now, at the time of the quantum supremacy, the idea was at the end of the year, you would build a utility scale quantum computer, roughly 1 million qubits or so. And that's what, people were talking about and hoping to do. But you see that the actual progress has been much slower. So you're halfway to the end of the decade, and we got a factor of 2. Now it's improving, it's getting better, but it's really slow. And I'm going to say, given this progress we're making here, if you want to get to the 1 million qubits, I'm going to say personally that I will probably be dead by the time that happens. And I'm going to say most people in the audience will probably be retired by that happens. That's too slow. We want to make it go faster. Now, you can argue that, okay, we can invent things and the like, but keep in mind, scaling from 10 to 100 qubits, maybe to 1,000, is relatively straightforward than scaling from 1,000 to 1 million qubits. So that's the hard part. Okay, so the chance of us rapidly accelerating this progress, not so likely, unless you invent some miracle technology. And our position is that there's actually a miracle technology out there, and that's going to be semiconductor fabrication advance. For example, on the left-hand side, this is a 300 millimeter deposition tool by Applied Materials that we're using to develop advanced qubits. Next slide, please. So in this process, we're trying to improve every step, and we know how to improve every step. This is a slide talking about the main decoherence mechanism, which are interfaces between the various metals in substrate and air. The most important one is between the silicon and the metal. And you want to make that very clear. Now, what we've done at AMAT, for example, is we've used one of their advanced processes where they can clean off that surface in situ, in vacuum, and then deposit the metal on top of that so that you get a perfect interface, as shown by the TEM example here, showing a very atomically sharp interface. And this is what you want to make really good devices. Next slide, please. For example, we're trying to get rid of liftoff. So we want to use a deposition and etch technique to do that. That's how modern semiconductor devices are made. On the left is an example of a non-liftoff process we're using, aluminum, SiO2, a window in the SiO2, which is a via, which the semiconductor industry really knows how to do. Clean that, regrow the oxygen, put aluminum on top in situ, and then as the very last step, you remove the silicon dioxide to form a window junction, freestanding, to get rid of all the lossy SiO2. Here's an example on the right, a device that's made in collaboration with Academica Sinica in Taiwan. We've made some qubits that work this way. The yield is very low. The coherence is around 30 to 60 microseconds, still a little bit low, but we think using the AMAT process, we can make this much better, bring the yield up and get that to work. Next slide, please. Okay, now we have to figure out how to scale. The wafer scale integration we're going to do is the way we're going to scale. And this is very much in tune with the semiconductor industry. On the left here, you see someone holding a wafer scale Cerebrus AI processor. So the semiconductor industry is already doing that. Our device density is very low, so this is going to be a lot easier to do. Now, what we're going to do on the left and the right, we're going to have a blue qubit wafer about the size of a 300 millimeter wafer with about 20,000 qubits. That's going to be bump bounded to a wiring wafer given in red, where the wiring wafer does the escape wiring of the 100 or 1,000 or so wires from the qubit wafer all the way up to 3 Kelvin with some micromachining to make sure that it's thermally isolated. And then at 3 Kelvin, you connect that to some flex wiring to say CMOS control circuitry, either at 3 Kelvin, 50 Kelvin, or all the way up to 300 Kelvin, depending on the power of the CMOS that you can do. This way, you can integrate this in a nice 20,000 qubit module that can be tested and made fairly inexpensively. And then you can tile these together as shown on the bottom in order to make bigger systems. And we think we can do something like 160,000 qubits with a line or maybe serpentine in a single refrigerator, with 3 options to how to scale that up more like a million or 10 million qubits. Next slide, please. Now, one of the issues here is doing the measurement. And that's because right now people use a measurement chain that includes circulators and amplifiers that are centimeters across. If you need 30,000 of them, that's just a huge, huge number. How are you going to integrate that? And the basic idea here is we're going to use on-chip measurement system based on the resonator kind of readout, but with an on-chip phase qubit to detect the photons, and then using more of a classical kind of readout using a squid at 3 Kelvin to read out the device. It's in the paper. You can look up the references. The important point I want to make here is that this has been done by Robert McDermott's group, a co-founder, a collab. Measurement errors are about 1%. It works. It was the first try. It kind of worked right away. We know how to make this better. So, you know, we should be able to integrate this into it. It's going to take some work to do that. This is all possible. Next slide, please. Finally, I just want to say a big thing that really no one talks about is cost. Okay, and we have to think about the quantum supply chain, how we're going to do cost. The basic idea of this slide is, look, the semiconductor industry knows how to make these kind of devices. They know how to mass produce things in these clean rooms so that we can use the expertise of the semiconductor industry to make these devices, scale it up, makes a lot of wafers, make a lot of circuit boards the technology exists on how to do this. Okay, next slide. At that point, that's the end of mine, and now we'll go on to into the control section.
Right. Thank you so much, John. First of all, I wanted to take a moment and actually thank you, John and Masood, both for doing this webinar with us, but much more so actually also for the really great collaboration and partnership. And I want to emphasize here how important this is, because and this is very much related to this topic of this seminar, of this webinar. We're trying to build a very ambitious system here, 1 million qubit utility scale quantum computer. And I believe that in order for us as a community, not even just this consortium, us as a quantum computing community, it's incredibly important that we develop these deep partnerships between different companies, different experts, and so on. And so I just wanted to take a moment to appreciate this collaboration with HPE, Collab, and actually with all the other partners that John mentioned in the first slide that he showed. Okay.
By the way, I don't see your slides. You might want to fix this.
You don't see my slide. Okay, let's do this.
We see you.
And now?
Yes.
Okay, great. Okay. Great, because I didn't talk about the slides yet. But okay, this is the first slide following John's talk. So I'm going to focus on the control part of the stack and talk about some of the challenges that you see here on the screen, as well as other challenges that I'll mention as we scale from 100 qubits to tens of thousands and hundreds of thousands and million qubits. Okay, so before I start, just a reminder, what is the control system? So we are familiar with the quantum processor. This is the quantum part of the quantum computer. This is where the quantum magic happens. This is where the extra processing power also comes. And frankly speaking, this is also the hardest part. And John talked about it extensively, making better qubits, more scalable, fast QPUs. That's the hardest part. But there is another system that's connected to the quantum processor, and that's the control system. That's a system that's responsible to drive the quantum processor dynamics using high-frequency signals. So that's the classical hardware that controls the QPU and also measures the signal coming back from the QPU. And at Quantum Machines, we're developing this control system. We have a platform called the OPX platform. Our core technology is this path processing unit that you see here on the slide that's embedded into the control hardware. And that's a full processor. That's a classical processor that we believe the architecture of the classical processor that is required to communicate with the quantum processor. And we have a programming language that we call QA, which is an easy and productive manner to describe and program what you want to run on your quantum processor. And so this quantum control system has 5 major roles, and these are also the big challenges that one needs to think about as you think about scaling. The first one is pulse generation and orchestration. You need to generate many pulses, many control channels as you scale up. You need to do qubit readout. So again, measuring signals coming back from the quantum processor, processing them to get the state estimations. Then real-time processing and decision-making. This is really what at Quantum Machines we're putting a lot of emphasis on. We put classical compute engines directly in the pulse processing unit, in the same FPGA, in the same processor that's doing the pulse generation and the qubit readout. We put this classical compute engine so that we can do real-time processing and decision-making and closing this quantum classical loop very tightly between the control system and the quantum processor. The fourth element is integration to external classical resources, which I'll talk about extensively. And the final element, which is very important, is the software interfaces. Again, we need very easy to use, easy to develop software interfaces, but also very flexible and expressive software interfaces that allow us to describe what we want to run on the quantum processor, and also software interfaces that allow us to integrate with the rest of the data center or HPC software components. So we're saying, okay, at the 100 qubit level, there are two elements that are very important. This is to speeding up calibrations. And if you click, you see these examples from Seoul University and from the Dave Schuster's lab, where we can actually do it, what we call embedded calibrations, where we continuously retune parameters on the fly, even kind of below the hood, and very quickly, so that we can prove calibrations. Even on the 100 qubit level, the calibrations are very complicated and take a lot of the time. As Masoud mentioned, system parameters keep drifting, and as we scale up, we need to push further on this. The other element is feed-forward based protocols. By doing, again, this quantum classical loop very tightly, one can create, for example, highly entangled states very efficiently using mid-circuit measurements, classical processing, and feed-forward response. If you can click. But okay, this is at the 100 qubit level. But now we want to go to the thousands and thousands of qubits level. We need to push on three different layers. First of all, scaling. We need to make denser and denser control electronics with lower and lower cost per qubit control. Then we need to increase fidelities. We do that by providing better and better analog specifications. And specifically, as we scale, we need to focus on the analog specifications that the qubits really care about. As John mentioned, the qubits are going to get better, and we cannot limit from the control system the fidelity. So we need to identify what are exactly the right analog specifications that the qubit care about and push on that. And the last element is classical resource integration. So it's great that we brought classic compute power into the heart of the control electronics, but to do quantum error correction at scale, for example, and other applications at scale, we need also to integrate now with the full high-performance computing system. We need external accelerators that are not in the control system and provide much higher compute power and integrate with those. Click. So in 2019, we launched our first product, the OPX, and this was the move from general test equipment to a processor-based approach. You can click again. But in 2023, we made another big step with OPX 1000, which exactly brings those three levels that I mentioned to higher scale. If you can click. So we already made a big jump on density. For example, about 10 times factor of density, and also significantly less cost per qubit control with OPX 1000. We also significantly enhanced the analog specs. Here you see an example of phase stability. It's not just the specification for a single control of a single qubit, a single channel. Also, when you scale up, sometimes you have these analog specifications that need to be great across the entire system, and that brings another layer of a challenge. And here, for example, you see phase stability across distant channels in the control system. And finally, with the work we're doing also with NVIDIA, integrating to HPC, we created a low latency link between the control system and the NVIDIA Grace Hopper platform. If you can click, sorry. So here we made this link based on very deep analysis. Here you see results both from 1QBit and from our research at Quantum Machines on the throughput that's needed and the feed-forward latency that's needed, for example, in large-scale quantum error correction. And that's how these are the requirements on which we're basing the interface to the decoder. So for instance, with feed-forward, you need to be able to close the quantum classical loop within 10 microseconds, and that's where we're going with this low latency link to the CPU GPU platform. Can you click? All right, and this is the full vision, how you connect the control system to and essentially the QPUs. So you see on the right side, the control systems are connected to different QPUs. And on the left side, you see how it's connected to the HPC system. Specifically, you see something very interesting here. You see the two networks, the blue network and the red network. The blue network is what we call the quantum error correction network. This is the low latency, microsecond latency network that we've already demonstrated with DGX Quantum. So you see we link the controllers to the acceleration servers with CPU, GPU, or ASICs down the road, or FPGAs. You can click again. All right, but how do we go now from 1,000 qubits beyond? We want to go to 10,000, 100 qubit, and even more. So at here, it's a question mark. We have to be also very honest and realize that some of the questions are still very open. So here we just wanted to share with you some of our thoughts. When we go to 10,000 qubit level, we believe that, okay, while the OPEX is ready for a few thousands of qubits, to go to 10,000 or 20,000, as John said, this is our benchmark. We want to make these tiles of 20,000 qubits. We need to make CMOS ASICs at either 300 Kelvin or 77 Kelvin with lower power consumption, lower cost. And these will be connected through high-density cables to the wiring chip and then the qubit chip, as John mentioned. And we believe also some moderate frequency and time division multiplexing will help here. If you can click again. Finally, if we want to go to 10,000 qubits and beyond, so here it's even more open. We don't know all the answers, but we believe that it's very important to explore lowering the control electronics temperatures even down to 3 Kelvin. Then you can completely remove the interconnects and the cables and do massive scale up. But if that doesn't work, we think you can still do it at 77 Kelvin with some more frequency division multiplexing and very importantly, a modular approach. As John mentioned, we can sort of copy paste what we do on the 100 or sorry 20K level to get to a much larger scale. So if you can click one more time. So in summary, the control hardware, there are many challenges. There are different solutions to different scales. And very importantly, we need to lower the cost because the control electronics can become the major part of the cost of the quantum computer. But we need to do it only when we are very fixed on the requirements and the architecture. So we believe that at the 1,000 to 10,000 qubit level, it's very important to, as John mentioned, improve the qubits, make sure that the fidelities are good, make sure that everything works, and then you can really, really scale up with, CMOS ASICs technology and bring the cost down and the scale up.
Am I sharing? Hello?
Yes, you are.
Okay. So while Jonathan is getting back online, it seems there was some service disruption on his side. So let me go to kind of discuss our software and algorithmic challenges. So as we scale from hundreds of qubits to millions of qubits, there are various challenges, and I'm going to focus here on how to perform distributed quantum computing with HPC integration. So, so people have been speculating about applications of quantum computing for years, and the discussion is always landing on certain application like discovering new drugs, discovering new science, discovering new materials. And this has always been projected to be 10 years away. And that was true even 20 years ago. And we are still not seeing any of this application. So what I should mention that the notion of utility scale quantum computing is it's that you run some quantum computer to solve a problem or model something which is faster or better than than classical computers, but it also is more cost effective. I'm coming back to this benchmarking at the end of my talk. So what happens is that today we have NISQ processors that are kind of small and noisy. We have around 100 qubits, but for any realistic application, we need 10,000 variables. So we are much short in kind of in a sense of like what the supply is in a sense of number of qubits, and you cannot increase the NISQ beyond that because of the errors, the coherence effects that are going to catch up with you. So you need to potentially create a network of hundreds of NISQ QPUs to maybe do something. I'm going to get back to this, what that means. But if you want to, and people argue that this is not the way we should go, and we should build a fault-tolerant quantum computer using quantum error correction. But despite all the excitement about error correction, what we have today is just barely a single logical qubits, which is, at the experimental level, it's not really like a technology, even at the single qubit. And if you want to do anything realistic, as I'm going to discuss later, you need at least tens of millions of physical qubits, and we are nowhere close to that. And based on pretty optimistic kind of projection for at least superconducting qubits, you can place on the order of 100K in a single dilution refrigerator. And so if you want to do error correction, let's say surface code quantum error correction, you need to have a distributed quantum error correction. So you need to connect hundreds of these FDQC QPUs. And so it means that we might need to have an integration with HPC infrastructure, whether for NISQ or fault-tolerant quantum error correction, because the QPUs are never going to be big enough for a full-scale standalone quantum computing. So you need a very tight integration with HPC. So our effort at Hewlett-Packard Labs is basically structured in this way that we have formed a team, we call it Emergent Machine Intelligence. This is a general physics-inspired heterogeneous HPC, which we tackle scientific computing. We are interested in solving complex reasoning and ultimately building world models for generative AI. And the HPE quantum team is being integrated here. So basically, we have two kind of big mandates on quantum side, which we are developing a unified workflow environment for easy use of quantum computers. Basically, it's like one single API to use any quantum computers with any quantum SDKs. On application, we are focusing on quantum data, quantum simulation, quantum machine learning on quantum data. And then we are also having a significant effort on quantum-inspired computing for optimization and sampling. In particular, we are applying those kind of techniques for augmenting large language model for complex reasoning. So we're adding these energy-based models or explicit system to thinking. So this is a large collaboration within HPC and with our partners that John mentioned earlier, in particular Quantum Machine, Colab, 1QBit, Synopsys Applied Material, and NVIDIA. So how should we do this quantum computing HPC integration? So at the top layer, it's kind of a more obvious integration that you have HPC infrastructure, you want to run some algorithms or you want to solve some problem. You use the existing HPC system, but you might want to call a quantum computer some of the time. And that's kind of the one layer of integration at the top level that we have addressed. But a more non-trivial thing would be how to distribute workload across various QPU, as I argued, because the size of QPU for our career time, as John mentioned, or some of us for our lifetime would not be big enough to do they're not going to be able to do computation at the scale that we need. And the lowest level close to the hardware, there is a quantum control and calibration that needs a tight integration with HPC, which Jonathan is going to talk about if he gets back online. So if you want to think about this a bit deeper, you realize that if you want to integrate fault-tolerant quantum computer, there are other layers of HPC integration that you have to consider. So I already talked about the top layers, which is just running a quantum computer as a subroutine, and a circuit knitting or hypervisor that do workload as distribution, which I'm going to talk about later in detail. But you need to also tackle tight integration with the kind of software stack for quantum error correction. So basically, you need to have a quantum operating system, which includes a compiler, assembler, and emulators. I'm going to discuss it later. And that needs a tight integration with HPC, but you need to be able to perform a distributed error correction, basically having this topological surface code distributed across multiple dilution refrigerator. You need ultra low latency real-time decoders. And at the lower bottom layer would be calibration and control. So here in this consortium, number 1 and 2 layers are entirely HPE contribution. 3, 4, and our collaboration with HPE and 1QBit, and 5 and 6 are more collaboration of HPE with Quantum Machine and NVIDIA. And also, of course, with Colab at the hardware level, number 6. So here you can see the connection in this full soft quantum HPC stack that you see at the top is that your own application could be machine learning optimization simulation. And then below that, we have this HPC programming environment. We develop a quantum interface library that you can easily run various different quantum SDKs and supports various different programming language. Below that would be adaptive circuit knitting that I'm going to discuss later. And we have various different extensions of this Cray programming environment for hybrid quantum classical computation, which can support various different, it's basically software and hardware agnostic. So if you look at the lower layers of the stack, there's this fault-tolerant quantum computing layer. Of course, you can consider a NIST layer for error mitigation, but I'm going to focus on the quantum error correction. So you need a quantum operating system, consists of compiler, emulator, assembler. The compiler synthesizes optimized circuit, consists of multi-qubit lattice surgery. Emulator basically uses the hardware noise model to infer logical error rates, and the assembler performs zoning, memory allocations, and detail of the schedules for lattice surgery. And then you have this real-time decoder on DGX Quantum, which Jonathan is going to talk about. And the calibration is below that. You have to do calibration because of this TLS and various different noises that could change in time. You might be able to, you need to do calibration quite frequently, and that's a huge challenge in scheduling works across different quantum processor. Below that, you have a heterogeneous system that you have various different CPUs, QPU, GPUs, and probabilistic processing units, and various different species even of quantum processing units. So on the application, I would just want to emphasize that we're looking at the things that you have a significant quantum advantage should be much better than quadratic. This is usually available for quantum data, either one you want to simulate it or you want to model it. These are two sides of the same coin. Basically, one is a forward problem of simulating something using some first principle knowledge, or the inverse problem of you have some data, you just want to build a model of that that can generate that data. And for quantum data, it's just for some general arguments of just storing it. There's exponential hardness in many cases when you have larger scale quantum correlations or entanglement. There are other applications that people consider in, for example, in discrete optimization, financial modeling, solving differential equation. We believe these applications are much less likely for real quantum advantage, because usually you need to load a lot of classical data on a quantum computer that washes away a lot of advantage, and most of this becomes something on the order of quadratic, where the overhead of our correction would basically diminish that kind of a speed up. So to actually look into closely of one of these promising ones, which is quantum simulation, one is electronic structure calculation for chemistry. So this is, you can do design at quantum scale. So so sometimes you have to design in molecules, you have to go in labs, you do have to do a lot of hard kind of experiment to just collect some data to see if some candidate molecules is good. But you can, do, for example, machine learning and build a model that can predict that. But you don't have the data. You can generate the data on a quantum computer by doing electronic structure calculation. So we looked at the two molecules that one is parabenzine, which is kind of fairly a small molecule. It's still classically simulatable, but it's a good start. So we looked at up to from 6 to 26 orbitals in the active space. We also looked at the FEMOCO. This is much bigger molecule with active space of 76 orbitals. This molecule is a very interesting one people consider as a testbed for like utility scale quantum computing resource analysis. It's kind of a cofactor for an enzyme that plays a role in nitrogen fixation, converting nitrogen in atmospheric nitrogen into ammonia. And people consider this as a real practical application if you can simulate this system efficiently. So we did some resource analysis using the TopCAD. This is the toolbox that 1QBit provided for us. And in collaboration with them, we studied various different scenarios. We studied sensitivity analysis of various different hardware that exists and or Colab is going to provide in the near future. But also, we looked at kind of how much the space-time resources to simulate these molecules. So in horizontal axis, you can see the number of orbitals from left to right increasing based on different approximation of the active space of these molecules. For these two molecules on the left is the p-benzine, and the right is FEMOCO. You can see that run times could be on the order of months to years. So actually could be in certain cases in the order of weeks. If you do some empirical trotter approximation, but there are kind of this double factorization, qubitization, which is much more efficient. It's this circle lines. So there are three colors of baseline, target, and desired baseline is what we have today, the existing hardware parameter that John described. Target is what Colab and John believes that those are realistic target that we can build in near future. And desired would be the optimal hardware characteristic. And you can see that by improving hardware and software, you can get orders of magnitude improvement. But still, the number of physical qubits will be on the order of tens of millions for simulating something like FEMOCO. I should tell you that the baseline classical, the gold standard is full configuration interaction, FCI, which you can see on the left-hand side is the dashed line. That is basically, you can see it's almost, strictly as exponential, and you cannot get more than 30 like orbitals. With DMRG and other approximation techniques, you can get up to 50 like orbitals, but we believe that if you want to push, as you push through 100 orbitals, quantum computers would be the only game in town. So going back to our software stack, you see that this kind of one actual use case, which would be electronic structure calculation for our smallest molecule that are beyond classical, it's tens of millions of qubits. So how can we avoid this kind of significant demand for a number of physical qubits by some algorithmic trick or some architecture that allows us to use the existing machine? So what we are thinking is about breaking down a quantum circuit into sub-circuits. So this is a partitioning a quantum workload. So there's a technique known as circuit knitting, which involves a cutting and basically knitting procedure. The cutting is that you look at a place between to identify two sub-circuits that you have minimal number of 2 qubit gates that has to be cut or severed. This is based on a quasi-property decomposition, which says that you can sample the entangled states by some local operation with some classical post-processing, basically some sample complexity. Unfortunately, that grows exponentially with the number of cuts. So what we develop is adaptive techniques that you can actually bypass in some realistic situation, this exponential classical post-processing by having some trick to look at the entanglement heat map. So what we do is that for example, we start with the tensor network ansatz. We do some random cuts. We allocate the different partition of this problem to different QPUs, and we use a quantum machine learning, variationally learning the circuits that realizes these QPUs. But then with the auto loop mechanism, that's a classical machine learning, we can find the optimal cut. The signal comes from some measure of entanglement. Basically, when we look at the entanglement heat map, we can identify these kind of opportunities. So this is example, for example, for a 1D transfer sizing model in presence of a strong disorder, that you can see a simple load balancing cut is not optimal, and you were going to cut at like a high entanglement boundaries. but you can identify these low entanglement boundaries and do adaptive cuts. And we showed that for like 32 qubits with just single cut, you can get even a 2 order of magnitude reduction in sample complexity. And we expect that the improvement grows as you have more a bigger system, and you employ more cuts, and the system is a high dimensional. So in the last piece, I want to say that if you even want, not only that for building a quantum computer, you need to do HPC integration, but also for benchmarking it, you will need to do that. Why? Because this quantum algorithms that would be efficient would be heuristics in all cases almost. Unique, you cannot provide any bounds. So what you need to do as a baseline to run the state-of-art classical solver on a state-of-art heterogeneous HPC infrastructure, including physics-based classical computing accelerators like FPGAs, custom design ASICs, and those could give you even like 5 order of magnitude improvements over like a naive or these baselines that people consider on digitally on like CPUs. So if you consider that infrastructure if you add quantum computing, basically some QPUs, you can ask one of these two questions. If the answer to either of these two questions is it's basically yes, then you have a quantum advantage. The questions are the following. After adding quantum QPUs, does it provide a better solution model in a given time and cost budget? Or does it match classical performance in a shorter time or in a cheaper fashion? If the answer is yes, you have quantum advantage. If not, just remove the QPUs, and what you already had as your baseline is basically the state of art, and you can also ship that and monetize the baseline as the best physics-inspired solvers and machine learning models.
Okay, so thank you very much. I just want to give a conclusion slide here. And we think there are just significant challenges in both hardware and software to build this. And I would say, minimized or overlooked by many of the projects out there. And we think that the key idea here is to leverage the expertise of the semiconductor industry, because they know how to build things quickly, reliably, and lowering the cost. We're going to talk, we talked about performing distributed quantum computation, integrating with current HPC. We've given detailed resource estimations, which we can understand what we have to build and plan for that using quantum chemistry and other algorithms. So that's really important to figure out what we have to build. We have an active consortium, both from hardware to software, and also with different consortium members such as companies, startups, national labs, universities, which we think that is a very powerful way to put this together to address the problems, solve them, and do this in an efficient way. And I hope this motivates you to look at our long position paper. I think it's 75 pages now, where we try to detail this, at least understand some segments of this for your particular research effort. And we think this kind of paper is what's needed for the different qubit modalities in order to make good progress in the field in the next decade or so. So with that, thank you very much for your attention, and I think we entertain questions at this point.
We are pretty much out of time, so I suggest that I'll take the questions we have and just distribute it to you guys to ask great speakers, and anyone that have any follow-up questions, again, forward it to me, and I'll forward it to the speakers. And at this point, I'd like to thank our speakers for a great presentation. Thank you, John. Thank Masoud. Thank you, Jonathan. Thank you all for joining us today.
Thank you so much.